This example will illustrate the methods required to use a compound pulley system where there is a rolling wheel on an incline. A block of mass 6 kilograms is attached to a non-uniform wheel that has a hub and is rolling on the edge of the wheel. The wheel has mass 2.5 kilograms with an outside diameter 50 centimeters, hub diameter 30 centimeters, and because it is non-uniform, the moment of inertia is given 0.075 kilograms square meters. There's a compound pulley system. There's a system of 2 pulleys here. And the pulleys and the string all have negligible mass, and the wheel rolls without slipping. We want to find the resulting acceleration of this object, block A, and the acceleration of the center, linear acceleration of the center of wheel B, and as well as the tension in the cable attached to the wheel. And so first, using the compound pulley system, if we call this cable tension T, the tension in the cable attached to the wheel, that means then that both of those 2 cables that are on either side of the pulley both have tension T, which means we have tension 2T at that location, assuming that pulley has negligible mass. And so we have a 2-to-1 mechanical advantage with this pulley system. The first step in any physical problem is to draw a picture. The picture is given. Step 2, we need to label positive directions. In order to choose the positive directions appropriately, we need to know which way the system moves. So we have to answer this question: which way does the system move? And the way that you answer this question is by calculating the moments that are acting on the rolling wheel. This wheel is going to be rolling about the point of contact, point P, which is at the bottom of the wheel, the connection point between the wheel and the surface upon which it rolls. And remember that we have been given the outer diameter of the wheel is 50 centimeters, so its radius is 25 centimeters, and the radius of the hub is 0.15 meters, half of 30 centimeter diameter. On the wheel, there are 2 competing loads. The tension is trying to pull the wheel up the incline and give it a counterclockwise spin. The weight vector acting at the centroid of this wheel, point B, acting straight down. If you resolve it into its components, there will be a component along the incline which is going to act and cause around point P a clockwise moment. So if we look at the moments on the rolling wheel, and if we look at the moments up the incline, we're talking about the tension acting at a distance of 0.4 meters. So that tension pulling up the incline acting at a distance of 0.4, so 0.25 plus 0.15 is the distance from where the tension acts to point P. That will give us a counterclockwise rotation, but we don't know what that tension is. So our first guess for that tension would be related to the weight of this block. If the weight of this block is sufficient to just make this roll up the incline, then this tension will be slightly less than the weight of this block. If the block actually ends up rising, then this tension here is going to be slightly bigger than the weight of that block. So a first approximate guess would be this tension 2T will be approximately equal to the weight of that block. So if 2T is the weight of the block, then 1T should be half the weight of the block. So if we take MAG over 2 and multiply that by 0.4 meters, that'll work out to what's that? 6 times 9.81 kilogram meter per second squared over 2 times 0.4. We're going to end up with about 11.772 Newton meters counterclockwise. If we compare that now with the moments down the incline, if we take the weight of this wheel down the incline, that is going to be approximately mbg sine 30. The sine component is the component that is parallel to the incline. If we multiply that by the distance from where that centroid force acts to point P, it is 0.25 meters. And if we plug those values in, mass being 2.5 kilograms times 9.81 times sine 30 of degrees, which is a half, times 0.25, we get about 3.066 Newton meters clockwise. So obviously this one wins. It is much bigger than this one. They're not even close. And so the wheel, our conclusion is, the wheel must roll up the incline. And therefore the block must fall. So if we let acceleration A be the unknown acceleration of the block, then I'm going to choose, since it's moving down, I'm going to choose positive y direction to be downward for that object. The cable tension. The cable is going to be accelerating up the incline, but because of the mechanical advantage, if we get one displacement, velocity, or acceleration output on this side, we must have to have two acceleration, velocity, or displacement in order to maintain conservation of energy. Basically, two tensions times one displacement has to equal one tension times two displacements. And so the linear terms are double on this side of the compound pulley system. So therefore, I'm going to choose the following coordinate reference frame. Parallel to the incline, up the incline is positive x for the wheel, perpendicular to the incline is positive y, and rotation counterclockwise is positive for the wheel. So step 2, label our positive directions. That's done. Step 3 is to list our known and unknown quantities. Well, going to the question, if the block has a mass of 6 kilograms, then MA is 6 kilograms. The wheel has a mass of 2.5 kilograms, that's mass B, 2.5 kilograms. The radius of B is 25 centimeters, and the radius of the hub is 15 centimeters. So 0.25 meters and 0.15 meters respectively. The moment of inertia of the object, of the wheel, it is a non-uniform object, so 1/2 mr squared is not going to work here. We are given the moment of inertia around the centroid for that wheel is 0.075 kilograms square meters. And we need to find acceleration A. We'll relate that to acceleration B, and we'll also find the tension in the cable. In order to find step 4, in order to find an equation that deals with these known and unknown quantities, you're not going to find one on a formula sheet. This means you're going to have to make your own. And the way that you make your own is with a free body diagram analysis and applying Newton's second law. So if I draw the free body diagram of block A has a single cable with two tension T acting up and the weight vector MAG acting down. And just as a reminder, I picked A acceleration down with positive y direction down. if I analyze that free body diagram, we have net force in the y direction is mass times acceleration in the y direction, general equation. Add up the vector components. We have MAG is a positive component. 2 tensions is a negative component because it points the opposite direction of positive. Completely independently of that, the mass in this diagram is mass A, and the component of this acceleration vector in the y direction turns out to be positive A. We have 2 unknowns, tension and acceleration. If I rearrange for A, I would divide by mass. If I rearrange for T, I divide by 2. So slightly easier to rearrange for T. And so we get MAG minus MAA is 2 tensions. And so tension should be MAG minus MAA over 2. Now I can leave it in that form, but you'll find that when we do free body diagram analysis with rolling wheels with hubs, there are a lot of constants that are different, and algebra can get kind of cumbersome. So I'm going to actually do this one numerically, and if I plug in these numbers, MA, which was 6 kilograms, 6 kilograms times 9.81 divided by 2 is going to give me 29.43, minus half of 6 kilograms is 3A. So this equation, even though I'm doing it kind of numerically, shows us that the maximum value for the tension can possibly have on that cable is 29.43 newtons. Because whatever acceleration I get, it's going to take away from that tension. So that's the maximum value for the tension in the cable. That's the tension that is required. It can't be any higher than that. It's going to allow block A to fall. If I draw the free body diagram of wheel B. So if we look at wheel B has both a wheel and a hub. The point of contact at the bottom of the wheel, P, is the instantaneous axis of rotation. The tension that is acting on that wheel is exerted from the top of the hub, but the surface upon which the wheel rolls is going to exert a normal force and a force of friction on that wheel. The weight vector is going to exert a force which is broken into 2 components. We have mBg sine theta and mBg cos theta, where theta is the angle of the incline. And the angle of the incline is 30 degrees, so that should be listed in our information here as well. So on this free body diagram, we have that the cable is going to experience an acceleration up the incline of 2A. In order to analyze this free body diagram, if we take net force in the x direction, we have tension is unknown, acceleration is unknown, and friction is unknown. But if we take moments around axis P, it eliminates force of friction, normal force, and mBg cos theta from the analysis. Only 2 competing loads cause rotation around axis P. And in fact, the same 2 competing loads we introduced at the beginning when we tried to figure out which way the system moved. So if we use, on the free body diagram of wheel B, if we use net moment around axis P equals moment of inertia around axis P times alpha. The two competing loads here are, because up the incline is our positive direction for rotation, we have tension acting at a distance, and now the distances on this free body diagram again are 0.25 meters for the radius of the wheel and 0.15 meters for the radius of the hub. We have tension acting at a distance from axis P, 0.4 meters away, positive rotation, that's counterclockwise, minus mbg sine theta acting at a distance of 0.25 meters. That's going to equal the moment of inertia around axis P is the moment of inertia around its centroid plus the mass of this object times the distance between P and the centroid. The distance between P and the centroid is or will be distance from P to C squared in general. It turns out to be 0.25. And then alpha is the acceleration of any known point on that object. The top of the wheel hub has an acceleration 2a, but the radius to the axis of rotation from that 2a acceleration is 0.4 meters. And so we end up with 0.4t, and if we put all these numbers in, mbg sine theta, we end up with that same result that we had here, 3.066 Newton meters. mbg sine theta times 0.25, so that's 3.065625 Newton meters. That will equal the moment of inertia around the centroid for this object, 0.075, plus mass B, 2.5, times the distance from P to C, which is 0.25 meters squared, all times 2a over 0.4. So we are left with 0.4 tensions minus 3.065625 equals, multiply this out, and we end up with 0.23125 times 2a over 0.4. Move the 3.06 to the other side and divide all terms by 0.4. We get an equation for tension, and it will be 2.890625a. So that's 0.23 times 2 over 0.4 divided by 0.4 plus 3.06 divided by 0.4 is 7.66406. So we have a few more decimals in here. There's a lot of algebra if we would have left it in algebraic form. But this is now telling us that the tension in the cable is a minimum of 7.6 newtons. It is required to be a minimum of 7.6 newtons to make sure the wheel rolls up the incline. If it wasn't at least this high, the wheel would not roll up the incline. So it can't be more than 29 in order to allow the block to fall, but it has to be more than 7.6 to allow the wheel to roll up the incline. So the tension is going to be between the minimum of 7.6 and a maximum of 29.4. Using the system of equations methodology, if we set these two tensions to be equal, then we have the result from the wheel, something like this, 2.89a plus 7.664. That's going to equal the result from the block, 29.43 minus 3a. Collect the a's together, and I get 5.89a is 21.766. Divide the two together and make sure I use my unrounded values for all of this, and I'll end up with 3.695 meters per second squared. This means that the acceleration of the block is 1a downward, so the acceleration of block A has to be 3.70 meters per second squared downward. And that answers part A. Part B, the acceleration of the center of this wheel is going to be directed up the incline. It's going to be a portion of this acceleration at the top of the hub. And so the acceleration of point B is going to be some multiple of 2a. But because point B is closer to the axis of rotation than is the top of the hub, it's going to be a multiplier of something less than 1. If we take the radius from P to C, 0.25, and divide it by the radius from P to the top of the hub, 0.4, we end up with this ratio, 0.25 on 0.4. And if you multiply those numbers out, we get 4.62 meters per second squared, which means the center of the wheel actually travels faster than the block. And that is, again, because even though the center is closer to the axis of rotation than is the cable, the compound pulley system doubles the linear motions. And so that direction has got to be parallel to the incline, so that would be at 30 degrees above horizontal to the right, or to the left. To get tension, we've got these two equations right here. So we can calculate part C, we can get the tension very easily. Tension is 29.43 minus 3 times 3.695, which gives us a tension of 18.3 newtons. But we can also check it. If we take this tension equation, 2.8906 times 3.695 plus 7.66406, we'll find that we get a tension that is also 18.3 newtons.